plus minus, m plus is some w plus module, m minus is w minus module of weight lambda. And then we consider m plus tensor some lattice and Heisenberg-Fock space, and this is a Heisenberg-Fock space. And consider relative semi-infinite cohomology of the space. And then we can define, this has some structure of w minus plus module. If you take w plus, and we get w minus module. And if you take w minus module, then we get w plus module. And we prove that this gives another definition of coset functor, 7141. And using this cohomological realization, we can prove that this functor gives isomorphism between space of logarithmic intertwining operators. And also, this has if the fusion rules were defined, then this cohomology functor factors this fusion's product. But this means that this cohomology functor gives a block-wise monoidality, because you see, for example, you see we consider m1. So mi is weight lambda I. So we need to consider m1 tensor m2 has lambda 1 plus lambda 2. So but this decomposes to cohomology for lambda 1 and cohomology for lambda 2. So these are different. These functors are different depending on choice of lambda. But anyway, we have these natural isomorphism. So plan is first I explained Y algebra and W algebra. And next explain my main theorem 2, 3, and 4 in the section dualities on W plus and W minus. And then I explained the applications of my main theorem. And finally, I give some comment on future works. Okay. So first, I introduce Guyot-Lapchak Y algebra and Lapchak Soiberman-Yang-Chao's W algebra. So we take LMN, this is some integer, and psi the scalar. As maybe in last time Thomas explained a little bit, explained that G of twisted n equal 4 super Yang-Mills KH theory gives some two-dimensional conformal field theory corresponding to some Vertex algebra named Y, L, M, and psi. And that motivated from the correspondence between the gauge theory to two-dimensional conformal field theory. And we have two dualities. One has some trivial duality. If we change m and n, we get change on n and n, then the psi can be changed to 1 minus psi. But we can consider S duality and the gauge theory. Then in terms of Y algebra, it becomes a change of L and M. This becomes psi, the psi inverse. And the Guyot-Lapchak conjectures using these two duality and get triarities. If you change LMN and NML and MNLN, and psi has been changed in this way. And the surprising result is Krutty-Green show proves that if one of LMN is equal to 0, this conjecture is true. It's a very surprising result, and I will explain this theorem first. So now take F is the nilpotent element in GLN. And this has some Jordan form. For example, this is a 6x6 matrix and a block, some 3x3, 2x2, and 0. And this gives this corresponds to some partition. In this case, it looks like some 3, 2, 1, 6. So I mean, this gives some nilpotent element can be classified by partition of n. And if we take P as partition of N, then we corresponding nilpotent element we denote by Fp. And we denote W algebra of GLN and P is defined as W algebra of GLN and Fp. This is defined by Green philosophical reduction of affine GLN associated to Fp. And similarly, we consider W superalgebra of GLMN for partition P and Q. And we get the corresponding Fp is nilpotent element in GLN, and Fq is nilpotent element in GLM, and consider Green philosophical reduction. And get we denote by this W superalgebra WK GLMN PQ. Then the Y algebra is defined by this formula. So if L equal to 0, this is a commutant of affine commutant inside W algebra of some n minus m 1 1 1 1 1. So this looks like some n minus m and 1 1 in this way. There's some hook type. Hook type partition, and secondly, and now we consider m equals 0 case. This is a fine coset but inside W superalgebra, and similarly n equals 0 case we have also defined by a fine coset inside W superalgebra. For example, if two of LMN are equal to 0, then we get W principal W algebra of GLN. We denote W psi GLN. And YN00 is affine coset in affine tensor L1 GLN. So, but LKG as a simple quotient of universal affine. And 0N0 is also principal. This is the principal W algebra. And Y00N is the principal W algebra. And so S duality on Y00N. So S duality is the first and the second subscript have been changed, but this is self-duality. But the psi has been changed, and this gives Pagan-Frenkel duality. And S duality between the changing n and 0, this gives isomorphism between this first and second one. And this gives a coset construction of principal W algebra, recently proved by Arakawa, Kritik, Rinshaw. And n equal 2 case principal W algebra of GO2 is just Virasoro algebra, tensor Heisenberg. So this gives some GKO coset construction of Virasoro. So now, so how to prove Gauss-Lagrange conjecture? So we recall geometric realization of principal W algebra. So now Mariko Konkov and Schiffner-Basel give some consider some affine Yangian action on some equivariant cohomology on some geometric object MRN. MR is some moduli space or some rank out torsion-free shapes on P2, such kind of with some framing. And then using this geometric description, anyway, we get some dense morphism from affine Yangian to universal enveloping algebra of the principal W algebra. This gives some geometric realization of principal W algebra. But we have vertex algebra counterpart. So WC lambda. This is called range of universal two-parameter W infinite algebra, maybe known in physics, but we should define this WC lambda purely algebraic way. The point is this is some vertex algebraic version of affine Yangian of GL1 hat, and this defined by this is generated by Virasoro L and W3, W4, W5 and over polynomial C lambda with some relation. I will wrote these relations. And the point is this satisfies Jacobi relations. And the claim is all Y algebra if one of element is 0, can be realized some simple quotient of this WC lambda over polynomial C lambda over I. This I is an ideal. But these three algebra satisfy some nice property for generators that using the uniqueness of simple quotient forces isomorphism between three algebras. This gives a proof of triarity of Guyot-Lapchak. So this is a very nice proof. On the other hand, Mariko Konkov and Blavano, Pinkeva, Nakajima gives a different geometric realization of the principal W algebra. They consider G is ADE type and denote G this notation. T is just a torus. And they consider UDG, that's named Uhlenbeck space, some compactification of moduli space of G bundle over P2 with some term elevation, and D is an instant number. And then they consider intersection cohomology and consider these result. And they prove that this gives a geometric realization of screening kernel realization of principal W algebra. So first term is just identified with principal W algebra. The middle term is identified with the kernel screening operator. Last term is tensor of Heisenberg-Fock space. And Lapchak, Soyman, Yang Zhao generalize this realization using moduli space of spiked instant tone. I don't know what it means, but anyway, they can generalize these results, these construction, and get the W algebra, WLMN. And this is defined as a kernel of some screening operator inside the Heisenberg-Fock space. And also observation, geometric action, and they found some affine yang action inside, densely inside the universal empirical algebra with Stauch algebra. So natural question is this Y algebra is equal to W algebra. Naively, not really, but if a Semel 1 says 0, 1, if LMN equal to 0, 1 R case, this is true. The proof is using the screening realization of W algebra and checking their notation. And very easy, but anyway, we can prove this result. Okay. So, but in this case, so in screening charge is depending on alpha I, but this alpha I corresponding to simple root of G. And in our case, we want to consider 0, 1 n case. This alpha I corresponding to simple root of SLN1. So using theorem 1, W0, 1 n, this is this is isomorphic to now Heisenberg commutant of W plus, and Krutik-Renshaw, this is Heisenberg commutant of W minus. And this is by definition can be identified with screening kernel, and alpha is corresponding to thinking diagonal inside box space. But the screening operator is well defined in the some extended domains. If we replace this extended domain to Heisenberg tensor some lattice, and then the kernel of the screening operator gives W plus itself. And if you replace this domain to Heisenberg tensor BZ, then the kernel screening operator is W minus itself. So this means that the difference between W plus and the W minus are the difference between the domain. So this means that if you take W minus and tensoring some lattice and taking rank 1 Heisenberg, it should give some changing of lattice algebra in the domain of screening operator, then gives the isomorphism because they have same screening form. And also opposite is same, that we need to choose. We need to use different lattice vertex algebra. But anyway, this gives a proof of theorem 2. So example. So if you consider element equal to 0, 1, true case, W plus is just a affine SL2, and W minus is just n equal to superpure solo, or we call superconformal algebra of central charge minus 3 to L plus 1. So this duality between affine SL2 and n equal to superpure solo is a very famous duality, well known these people. Diverger Petersson U10 or Downbeach and generalized Kazama Suzuki duality, and the general case approved by rigorously by Krudik and Winshaw. Anyway, this is very well known, and the module of these algebra are studied by Fagin, Semikatov, Tipanin, and Ryosato. They consider category of weight module, and affine set module can be decomposed in this block, and n equal to superconformal algebra decompose this block. And as I explained firstly, we take tensoring some lattice and decompose to some Heisenberg action and some multiplicity space. And then this multiplicity space has a module structure. If starting S affine set 2, this multiplicity space has a n equal to superpure solo module structure, and the opposite is true. And this gives a functor omega lambda plus, and also in opposite omega minus lambda. And we can prove that they are inverse to each other, and this gives the equivalence of block categories. And our theorem is just a generalization of this result to subregular W algebra and principal W superalgebra. And we can prove that similarly blockwise equivalence. But the important observation is this cohomological approach. So we can realize this coset operation in terms of cohomology. So if we take, for example, W plus and tensoring lattice PZ and tensoring 1 Heisenberg, and then we consider relative semi-cohomology, then we get W minus. And if you start in W minus, we get W plus. And this gives isomorphism as a vertex superalgebra. And this cohomology makes sense in the module. So if you take M plus, this is the module or block corresponding to lambda. And then we can tensoring lattice and also Heisenberg, but some weight. Highest weight is some depending on lambda. I don't explain epsilon, but we can define relative semi-cohomology. And this, by definition, this has if you start in W plus module, by definition, this has a W minus module structure. And we can prove that this cohomology functor is isomorphic to coset functor. And if you take intertwining operator M1, M2, M3, then we consider corresponding to complex defining this cohomology, and then intertwining operator between them induces intertwining operator between complex between them, and we can prove that such an intertwining operator is well defined in the cohomology level. And we have plus functor, but if you use minus functor, this gives the opposite direction, and this gives the proof of isomorphism between two intertwining operator. And this isomorphism is induced from the complex level. So this induces some quasi-isomorphism between cohomology. So we can prove that some naturality by construction of this isomorphism. So So similarly, we can prove number 3 statement if you take the element and this element and taking fusion product and consider complex level and taking fusion product between complex and prove that in the cohomology level this isomorphism and prove that naturality. Okay. Is there any question? Okay. So I will go to application part. So now we have proved all theorem I stated in main theorem part. So we consider application. So now we denote W plus subscript K. This is a simple quotient of subregular W algebra. And W minus subscript L is a simple quotient of the principal W superalgebra. And we introduce WK prime SLN R is a simple quotient of principal W algebra. Then, first of all, we can prove that in the simple quotient level, we also have duality. I mean, our duality isomorphism is a factor to the simple quotient. And recently, we consider rational level. Alaka van Ekeren consider some interesting level. This is called some non-degenerate admissible level. Then they prove that subregular W algebra is C2 cofinite and rational in this level. But using this duality, this C2 cofiniteness and rationality inherit C2 cofiniteness and rationality in the super W algebra. Then we get the corollary 7. It says principal W superalgebra is also C2 cofinite rational, but find some conditional level. And also, in critical Green-Shaw, consider same level that now R is equal or greater than 2. Then the Heisenberg coset of subregular W algebra is isomorphic to principal W superalgebra, but SLR. So our W plus K is defined as a subregular W algebra of SLN. But now this isomorphism gives the principal W algebra SLR. R is appearing in the condition of level. So this gives a variant of level rank duality. So n equal 2 cases known Alaka Lam Yamada. N equal 3 cases Alaka critical Green-Shaw, but we are now general result. And we introduce a notation thanks to Frenkel, Katsuba-Kimoto, Arakawa, and Arakawa van Ekeren, and Krutik. There uses some nice correspondence between simple module of affine level n SLR and the simple module of principal W algebra of SLR. We denote by this correspondence L lambda and LW lambda. And they prove that there exists one-to-one correspondence between simple to simple, simple of affine to simple of principal W algebra. And this gives, this induces isomorphism of fusion rings. And so our theorem is if K, L, K prime are satisfying our rational level conditions, then we consider coset of principal W algebra inside the subregular W algebra. Then this gives a lattice lattice algebra, and can W plus decompose to these modules. And using this is, we can prove this result by using simple current extensions, and also combining dualities between W plus and W minus, we obtain the dual statement for W minus. This also W minus now decomposed to module principal W algebra tensor lattice lattice algebra modules. Okay. But using this correspondence, we obtain the isomorphism of fusion ring between affine SLR and subregular W algebra. And also, simple module of principal W superalgebra has nice description, a nice classification of simple module using this correspondence. And also, the second isomorphism in theorem 8 induces a nice description of fusion rings of principal W superalgebra. So first, number 1 in the query 9 is known for n is even case by Alka von Eken, but we generalize with observation. And second and third statement has been known for n equal 2 case for Adamowicz and Wakimoto, but now people more general cases. Okay. So finally, I give some comment on future works. So firstly, our result is very some special case that critical Renshaw consider more general case. They consider y m0n. Our case is just m equal 1, but they consider m0n and tensoring some a plus, and consider relative symmetrical homology. Then they conjecture that this is isomorphic to y0mn. But a plus is just a kernel VOA. This is some defined as some corner of VOA in the talk of Thomas. And what is kernel VOA? So m equal 1 case, we know this is our m equal 1 is our cases. This is just a lattice tensor Heisenberg, very simple. M equal 2. So by conjecture, a plus satisfying some form, satisfying these forms. But problem is there any vertex structure in this apex that Krutik-Kayotto shows that L1 D2 some minus psi inverse tensor Heisenberg satisfying this decomposition, and they said we can choose A plus as L1 D21 psi minus psi inverse. That m is equal or greater than 3, the existence. We also have some A plus should have some form as a module by conjecture, but we don't know the existence of VOA structure on this kernel VOA. So still very difficult problem, but very interesting question. And also using duality or triality statement, opposite this. We start y m0n and get 0mn, but if you're starting y 0mn tensoring some kernel VOA, also should give some y m0n, but in that case, some kernel VOAs are very difficult and not so known. Okay. The second comment is other type. I mean, we talk about A-type statement, but the Dirac introduced other type, type BCD and OSP. They denote such an algebra y plus minus and y tilde psi plus minus. And they conjecture that there is also triarities between this y plus minus and y tilde plus minus. And surprisingly also including Renshaw, if one of LMN is equal to 0, this conjecture is still true. And the proof is similar, essentially saying they realize this y plus minus and the y tilde plus minus algebra as a simple quotient of even spin two-parameter W-infinite algebra. A-type cases, they consider some WC lambda. This is some vertex algebra like interpretation of Fine-Yangian of GL1 hat. That is generated by Virasoro, W3, W4, and so on. But the even spin is generated by Virasoro and W4, W6, W8, so on. And they realize these algebra as a simple quotient with even spin W-infinite algebra, and also using the uniqueness argument forces triarity. So this is a very nice result. So the question is how about screening kernel realization? So in fact, we don't know except for some special cases. We study some special case is just SO W algebra of subregular W algebra of SO 2n plus 1, and we denote W plus K, and principal W super algebra of OSP 2 to n, and we denote WL minus, and we can prove that using the same argument, we have these algebra has nice screening kernelization and satisfying dualities. So we expect similar result, duality, cosine functor, and relative cohomology, and so on. But we omit such a statement. And other case, for example, C-type case also we can expect similar result, but we don't know how about it. This is still comment, just a comment. Sorry. So further comment is some degenerate case. So n equal 1. So n equal 1 case is identified with W plus is now beta gamma system, and W minus is affine GL11. And this duality is well studied. For example, Naoki Genra consider fusion rule of beta gamma modules using the fusion rules of affine GL, also GL11. So I should write GL11. Module. But in fact, the module of beta gamma system is very difficult, but the module of GL11 is well studied by Kutik and result and relatively easy. So that's the reason why they consider that they use such a duality and determine fusion rules. And also recently, Kutik McRyan consider Kazdan-Lustig category of affine GL11, and they prove that some Bray tensor category structure on this category and prove rigidity. So using this duality, we expect that we can prove Bray tensor structure on the module category of beta gamma system. And yeah, and also we can expect generalization. I mean, super module structure is relatively easy as W plus module, and we expect this strategy. For example, so if you consider n equal 2 case, we consider relative semi-infinite cohomology functor. And then we consider simple relaxed highest weight module of affine SL2. This is very important in the context of logarithmic CFT. And a simple relaxed module, for example, we can typical simple module is this one. And we can prove that this cohomology functor maps to this relaxed highest weight module to simple highest weight module of n equal to supervia solo. And so that highest weight module is very easy to deal. And in fact, Fan and Miras prove that space of interfering operator between simple highest weight module of n equal to supervia solo is finite dimensional. So that our factor the interfering operator, so we can prove that finite dimensionality of space of interfering operator between simple relaxed highest module of affine SL2. And natural expectation, we can generalize this result to more generally, I mean, subregular W algebra case, that this is some much more difficult question. And third comment is some special levels. So if you consider K plus n satisfying this condition, then subregular W algebra is called dp algebra for P is n plus 1. dp algebra is a chiral algebra of address Douglas theory of type A1, A2p minus 3. And this is known to be extension of NP tensor Heisenberg, and NP is that's a singlet algebra. There's also logarithmic CFT algebra. And the example is Pico 2 is a beta gamma system, Pico 3 is affine SL2 at level minus 4/3. And motivated by this extension, and MP is now related, corresponding to quantum group is called unrolled restricted quantum group. Aga, Krutik, Canadell part consider some prove that the braid tensor structure on some extension set category related to BP module category tensoring some Heisenberg module category. This BP module category corresponds to conjecturally correlated to this singlet corresponding to this MP module, and the BP module category will be related some extension of this module tensor, this Heisenberg, and they define such a extended category by using induction functor and prove that the braid tensor category structure on these categories. And in fact, they also prove that such a category is non-semi-simple. So this means that we expect the BP module category is a non-semi-simple braid tensor category. But so natural expectation is we will use dualities, and we want to change BP module category to super type BP module category and study such a super side and inherit such some information on this BP algebra structure. But this is also an interesting question. This is last slide, last comment. Sorry, so lots of comments. So, in fact, triality suggests more general dualities. I consider 0, 1, 10, but there is more general case. In fact, this is WSLN and N minus N1 and WSLNN and some reported. And Adamowicz considers embedding of a simple affine SL2 inside simple Virasoro tensor pi. The pi is trivial lattice tensor Heisenberg. And this embedding means that if you take module of simple Virasoro and tensoring pi, we get affine SL2 module. But this is very interesting because this gives some explicit construction of relaxed hybrid module of affine SL2. And in fact, we can apply this construction to compute the characters and fusion rules and so on. So natural generalization is we generalize this embedding to higher rank case. And the natural conjecture is affine SLN can be embedded in minimal W algebra tensor some pi, and SLN some hook type, and so on. And finally, we get the principal W algebra tensor in some pi for some level k. And in fact, n equals 3 case, this path is exists. Proved by Adamowicz, Carset without, and also Adamowicz, Krutik, and me. And we conjecture for general case. And so we expect this path is so useful to study logarithmic CFT, and using the duality. You see, this W algebra is appeared in this duality. So natural question is what happens in the super site in this path, and we want to study such a path, how to define such a path in the super. Okay, this is all comment, and thank you for listening.
So thank you very much. Any question?
this is just a naive question. So you have these non-semi-simple categories of representations, and yesterday your collaborator gave a talk about non-semi-simple TQFTs. So are these going to be something like the categories of line defects in those TQFTs, or is there a more subtle relationship?
I'm not familiar with TQFT, but yeah, for example, Thomas talked about such a relation, and also in the context, subregular W algebra appears, for example, BP algebra. And our duality suggests some superside also has interesting and relatively easy to treat. So I think it's maybe duality suggests an interesting relationship between TQFT and the super vertex algebra, but I'm not sure how it affects on the logarithmic field.
Thank you.
Any other question? Okay, we're coming back at 11 sharp, I would say. So just yeah. Also, there's a list. There's a piece of paper down there. You can sign your name on for today's dinner and Thursday dinner. So some of them have already done that, I guess.